You're on the argmin channel, Real Analysis, Lecture 26, where we'll be talking about function convergence properties. Let me plug in my tablet. Okay, so this won't die as I'm doing this. So, if you recall, last time we looked at different types of function convergence, and now we're gonna show why those two different types are interesting. Now, just so it's fresh in our minds, recall that if you have a sequence of functions, f of k, where each f of k has domain A mapping to codomain Rm, where A is a subset of Rn, then fk converges to some function f, either one pointwise, if for every value in the domain, if you generate a sequence, so if you pass it through the function, you get a sequence in Rm that would converge to f of x to some function. So the function converges at every point in the domain, or uniformly if the supreme, the infinity norm or the uniform norm, which is defined as the supremum over x in A, fk of x minus f of x goes to 0. Okay, and some examples. If we take this sequence mapping 0 to infinity to a real number defined as fk of x equals kx over e to the kx, then if you just let k go to infinity, the denominator grows a lot faster than the numerator, so eventually it'll converge to 0 pointwise. But if you look at the infinity norm, x greater than or equal to 0, for kx over e to the kx minus 0, that is just going to be this. It's going to be positive anyways, or non-negative, so we can drop the absolute values. And that is greater than or equal to, if you pick x equals 1 over k, ek 1 over k equals 1 over e. So if you look at the sequence generated by the supremum or the uniform norm, then fk minus f infinity does not go to 0, it just goes to 1 over e. So fk does not converge uniformly. Now let's look at an example that does converge uniformly. So take a function from the reals to the reals defined as fk of x equals x 1 plus k x squared plus x. Now as k goes to infinity, this denominator gets very large, so this will go to 0, and this x will just keep going to x. So it will converge to f of x equals x, And if you check for uniform convergence, we got fk minus f equals the supremum for x in the reals of x over 1 plus kx squared plus x minus x, which is just equal to this 1 plus k x squared. The denominator is always positive, so we can drop that. And the supremum, we'll take the positive values of x. So we can change that to this problem. Now, if we define gk of x as this function x over 1 plus kx squared, then we got that g prime k of x is 0 if and only if x is plus or minus 1 over square root of k. So when we take the limit as k goes to infinity of this gk function, we sub that in. And the reason we found the derivative equaling 0 is because we're finding a maximum to get the supremum. So the supremum is attained at 1 over square root of k, and subbing that into g of x, 1 over square root of k, it'll simplify down to 1 over 2 square root of k, and that goes to 0. So f of k, or the sequence of fk's, converge to f uniformly. Alright, so now you should have a good idea of how to show a sequence of functions converges uniformly or not. Let's talk about why uniform convergence is something that is a nice property for a sequence to have. And we're going to be relating it to continuity of the function it converges to. Uniform convergence and continuity. So there's this proposition: if the sequence of functions is in the space of continuous functions mapping A to Rm, and fk converges to f uniformly, then f itself is also continuous. We rewrite that. F. Proof. Before we do the proof, let's look at an example that we looked at before. For fk from the closed interval 0 to 1 to r, where fkx is equal to x r of k, we showed that fk of x converges to f of x to this function 0, 1, where x not being 1 is 0 and x equals 1 is 1, and this wasn't continuous, and that's because the the convergence wasn't uniform. All right, with that little example, let's now prove it. Now suppose that we have a function as in the hypothesis of this proposition, and that function converges to f uniformly. Now suppose there was a sequence in sequence AK in the domain A such that it converged to A in A. Now we claim that f of AK converges to f of A, which by the characterization theorem that we looked at means this would imply that f is continuous. So let epsilon greater than 0 be given, since fk converges to f uniformly. We got that the supremum norm, or the uniform norm, goes to 0. So that just means the limit of that, of the fk's, is f. So there's an n1, and the natural number is such that if k is greater than or equal to n1, then fk minus f infinity is less than epsilon. Okay, since if we take the n1th function in the sequence, it's continuous because it's in C. Each function in the sequence is continuous. So if you take fn1 ak, that sequence would converge to fn1 of A. So that gives us another inequality. K greater than or equal to n2, then fn1 ak minus fn1 A. I need more space, let me move this down. Oops, don't want that. Ooh. Okay. Is less than epsilon. Okay, now suppose k was greater than or equal to n2, then now we're going to show that f of ak has limit f of A by showing that their distance with the norm is less than epsilon, as usual with these proofs. So that is going to be less than f ak minus, let's not do too many steps at once. So here we're gonna subtract fn1 ak and add it in the middle, ak. I think I need more room. And then we're going to subtract fn1 of A plus fn1 A, and don't forget the minus fa at the end. So that is here, and this one is over here. Now if we group things together, like so, we have a sum inside of a norm, and so we can use the triangle inequality. F(ak) minus f n1 ak plus f n1 ak minus f n1 a plus finally f n1 a minus f a. All right. And that's less than, so from, let me see. From this, we get that this is less than epsilon, and from this, we get that this is less than, epsilon from this inequality, and lastly, we get that this is less than epsilon from the top quality. So let's highlight those so we know how they match. So that looks like that. And this inequality is going to be applied to here. So that's less than epsilon plus epsilon plus epsilon. Since we want it to sum to epsilon at the end, we can just change that to epsilon over 3. It still holds because that's still a positive number. So the n1 and the n2 would exist. So then, changing those, we now have that's less than epsilon. So f ak converges to f of a. Therefore, f is continuous. Okay, now I'm going to introduce a theorem, and we're going to prove it next lecture. And this is the completeness theorem. So you may be wondering what space of functions is complete. Well, if K is a subset of Rn and it's compact, then the pair of the continuous functions from that K to Rm equipped with the infinity norm is a Banach space, i.e. a complete normed vector space, where completeness means that every Cauchy sequence converges to a point inside of the set. So if you have any sequence from this set, then it will converge, and it's a Cauchy sequence. And if it converges, it will stay inside of the set. And completeness is one of those things that is nice. It's the thing that sets apart the rational numbers, the real numbers from the rational numbers. That's the property that makes reals the way they are. And you can apply that concept to function spaces as well. And that's it. Comment questions below, and like and subscribe.